G'day, it's Mr. Bennett here. Today we're going to be looking at implicit differentiation, which is exercise 3G. Now, the rule is shown here. So if we differentiate with respect to x a value, a term which has got y in it, then what we will get is n to the n minus 1, and then we do our dy dx. Now, we don't really know what y is. Y is a function that is with respect to x. So I'll just go through a couple of examples and show you. Now, key reason why we might do that is something like if we were trying to find the slope of a tangent on a circle, then because it's got x and y terms in it, then you'd have to actually differentiate it with respect to y. Okay, so that's when you use your implicit differentiation. So here's an example, like we did x squared plus y squared, and that's equal to, let's say, 16. If I differentiate that with respect to x, then we know that x term's easy, that just becomes 2x, and then the y term will be easy too. That would be just 2y dy dx, and that would become equal to 0. So therefore, if I rearrange that, dy dx, now the 2x goes across, becomes minus 2x, and the y goes down the bottom, becomes 2y, so cancel that out. So therefore our dy dx term would become equal to minus x over y. Now obviously if we're looking at a circle which has got a radius of 4 in this particular case, right, so let's say I knew that point there was minus 3, we know that minus 3 squared is 9, so therefore this is going to be the square root of 7. Okay, so we know that these two terms must add up to be 16. Alright, so if I put that in there, when x is equal to minus 3, so that would become minus 3, and then that's all over root 7. So the slope of the particular tangent at that point there would be 3 over root 7. Alright, and you could find the basic equation of that at any point. So if we're looking at when x is equal to 0, we'd expect our tangent to be horizontal, wouldn't we? So that case there, when x is equal to 0, then y would be equal to be 16, wouldn't it? Or y, actually y would be 4. So then that would give you 0, and then obviously at these points here when y was equal to x was equal to 4, y would be undefined because that would be 0. Alright, so that works in this particular case. Now, in terms of looking at doing some implicit differentiation, the sort of questions that you get are things like this. Okay, you'll get some term like this, x, y plus y squared equals 7. Alright, and then it asks you to implicitly differentiate that to find dy dx. So we've got to treat this term here special because that's got an f of x term and it's got a g term, as we looked at using the product rule. So I'm going to sort of skip some steps here, but if I did the product rule there, my f dash is going to be 1, so that's going to be 1 times by my g value, which is y, plus my f value x times by my g dash, which is going to be 1 dy dx. Alright, and then I treat this term over here separately. That becomes simply this 2y dy dx. And then this term over here is going to become 0. Now, the secret when you're doing this, the next step after you've done the differentiation there, is to now simplify it. So we bring all terms that don't have a dy dx to one side, and all the other ones we combine as a common factor. Alright, so because they're already on the side, I'm going to put them over here, dy dx. In this term here, I've got an x plus a 2y. Right, this term over here doesn't have a dy dx, does it? So we're going to bring that on the other side, and that's going to become equal to minus y. And then to find my dy dx, I simply all I have to do is, in fact, bring that bracket down the bottom line. So that becomes x plus 2y. So that's my dy dx using implicit differentiation. Let's do another example. Okay, let's do something a little bit harder. Let's say we had x squared y cubed plus 4x cubed equals 2y. Okay, again we're going to do implicit differentiation because I want to find my dy dx, which is the slope of the tangent. So again I'm going to use a product rule there. We've got one function there, our f. We've got our second function here, our g. That's two separate terms, so we don't have to worry about that. So using our product rule, we're going to get 2x times by 3y plus our f dash, our f of x, which is x squared. Our g dash is going to be 3y squared dy dx. Notice this term over here doesn't have a dy dx. Reason is we didn't differentiate the y term, we only differentiated the x term. Then we're going to get plus 12x squared equals, I'm going to put a dy dx here because we have to differentiate that. That becomes 2 dy dx. So treat it like an x, but every time you have to differentiate a y, put a dy dx there. Now I've got to bring all my dy dx's to one side and all my other things to the other side. So I might as well bring that over here. That will leave me with 2xy cubed plus 12x squared equals 2 take 3x squared y squared. Okay, and that's all dy dx. So I've just brought that term, just brought this term here across to the other side. Now the next thing I've got to do is simply divide that bracket down the bottom line. So therefore I can say dy dx is equal to 2xy cubed plus 12x squared take all over 2 take 3x squared y squared. So that's another example of implicit differentiation. Now, I just want to show you just a little variation that might help you understand this. If I got given something like, what was an example I'm going to use? If I got given something like xy plus y squared, and I differentiate that using my implicit differentiation d. Right, so that's going to give me a value which is, using my product rule again, it's going to give me x, so it's 1 times by y plus x times by 1 dy dx, and then that's going to give me plus 2y dy dx. Now the thing is, we don't know what y is in relation to x. Let's let y equal x cubed. If we did that, then that implies that dy dx is equal to 3x squared. Alright, so if I did this at this particular case over here, so if we originally put that that value into there, then I'd have x times by x cubed plus x cubed squared. So that would give me x to the power of 4 plus x to the power of 6. So therefore, when I differentiate that with respect to x, then that would give me 4x cubed plus 6x to the power of 5. Understand that? Now, if I also now import that into into this term up over there, let's do the black term, then I'd have y, so that's y, so that becomes simply, or let's write it out, y equals x dy dx plus 2y dy dx, and that becomes equal to, well you know y is equal to x cubed plus x times by dy dx. Now we know dy dx is 3x squared plus 2 lots of y. Now we know y is equal to x cubed times by dy dx, which is 3x squared. So if I simplify that, that gives me x cubed plus 3x. Now x times by x squared is x cubed. And then we've got 2 times by 3 is 6. X, we add the powers together, x to the 5. And then that gives me 4x cubed plus 6x to the 5. So what it's really saying there is we can differentiate this without actually knowing what our y value is. But if we knew what our y value was, we can then substitute it in afterwards and then we'd find out what the value is. So hopefully that helps you when you're understanding the terms. Now, if you just quickly review what we had to do, okay, so we basically differentiate every term. Every time we differentiate with respect to a y term, what we do is we put a dy dx. So if we've got two functions like that, and quite often you get to use the product rule or quotient rule in these questions. And then what we do is our second step, so that's our first step, is to do that. Our second step is to bring all the dy dx terms over to one side. That's what we do over here. And then our third step is to actually divide that down on the bottom line. Now the other thing is, if we knew what our x and y values were, we could put that into that equation and we could actually work out what the exact slope is. So anyway, have a go at exercise 3G. It's really, again, it's a technique. Once you learn it, it should be pretty easy to do. All right, so I'll talk to you in class.